Thank you very much for the opportunity to give a lecture in this occasion here, especially with you in the audience. The topic of my talk is concerned, in fact, with a very special example, and the question in what respect the principle of functoriality is valid or not. And the case I'm considering is a small case of a small group. It's the group of symplectic similitudes in 4 variables. So this is a group of matrices, 4 by 4 matrices, which preserve a standard alternating 4 by 4 matrix with this symplectic structure with a similitude factor. And as for every reductive group over a number field or global field, we can study automorphic forms, automorphic representations. For the purpose of this talk, I will be exclusively interested in space and this cuspidal space of L2 functions. Cuspidal means strongly decaying forms. I also work for simplicity over Q. It's not important for this talk. And here there's the ring of adeles. I don't use classical language, but if you are not familiar with this, you could also think of R-valued points, and here points, let's say, in subgroups of the set-valued points, and take a union over all subgroups of finite index, which essentially is the same. This has the profit that in the language of adeles you have a nicer principle of local global arguments, which allows you to argue with points of the groups over fields instead of indexes. So whatever this is a ring. Who is not familiar with that? So I also impose a certain condition which is necessary but not important. And there's a certain central character. So on the center of the group, which is the group of diagonal matrices, you impose a certain condition. So this is a nice Hilbert space, and the group acts with ideal value points from the right. And it is well known that the space as a module, as a unitary representation of this decomposes into a direct sum, Hilbert space direct sum, to be precise, of irreducible representations of this group. And because A is almost a product, this is a restricted product over the completions of Q, p-adic completion of v-adic, could be also real Archimedean place. This is a tensor product, which is an almost tensor product, to be honest, of local representations, and these representations are representations of these completions, p-adic fields or the real numbers, into a Hilbert space as a unitary representation. I only write here E, this is a vector space over C. I ignore that it's in fact a unitary representation. It is not important. For the sake of this talk, and this representation has a property to be smooth, so it's a weak topological continuity property, which I'm not going to explain here, but is a technical notion which is not important for this talk. So if you look at this space, if you look at the spectrum here, this is contained in the discrete spectrum. This is strongly decaying, so representation here theory is much like on a compact group, so that's the behavior you have. Here you have also a continuous spectrum, which is much more complicated. also other parts of discrete spectrum, which I don't discuss here. This space of cuspal spectrums, or the set of irreducible representation that occurs, the points here I illustrate by this diagram. So I divide it into two halves. One of it behaves nicely to a lift. So this is this group GSP4. This behaves nicely with respect to a lift to a theta lift to GSP3, what is essentially quotient of G4 plus G1. And you have, this is not a theta lift, you have a theta lift from here to here. I don't explain what it is, it's just a procedure to bring irreducible automorphic representations, which are cuspal, from here to here. You do the same for this group. We take a similar space of cusp forms on this group. And this is by the trace formula. I don't explain how this works. It's unimportant for this talk. It's a procedure which makes out of objects on this side, at least on the right half, it produces cusp forms here. This side with cuspal spectrum here. Then we have two other parts which are coming from these groups, or for simplicity, I'm a little bit imprecise, but it should be also okay for this talk. You have also some lifts going from here to here, which are also theta lifts. And what you get here is a group of endoscopic lift. And here certain lifts which go via cup representations, which is Saito Kurokawa. Is the lift coming from, from here, and there's also a lift studied by Sutri, which is coming from here, or inner forms of this, similar to here. So for simplicity, I only write the split guy. So this whole spectrum is divided in basically its three parts, and there's a subsection which consists of so-called generic representations. And what I get from here, what I get from here are generic representations here. I don't discuss whether it's all, it should be not all, but almost every representation should be generic here on this part. This is a double point which I ignore, which is not important, which is understood by trace formula arguments. It's not the issue for this talk. The representations here are either generic or not generic, so both. But these guys here, this whole group, is not generic. Whatever generic is, I explained what generic is. These are non-generic and non-tempered. So what does it mean? To be generic is a condition which I will explain later. Being non-tempered means in a global setting that so-called Ramanujan conjecture doesn't hold. In a more intuitive way to say it, it's representations which are not bounded in a nice sense. One has to make this precise. I don't want to make it precise. I just want to emphasize that representations are divided in groups by behavior with respect to their boundedness of matrix coefficients of the representations, and this the notion of temperedness or non-temperedness. These are non-tempered, but they are very interesting because they were first found in the case of GSP4, and they're conjectures of authors who describe these non-tempered representations conjecturally in the cuspal spectrum. These are also lifts which were found by Langlands in the study of trace formula and stabilization. They have to occur by trace formula reasons. And the philosophy, they also correspond to lift, so-called stable lift. To analysis of trace formula, in fact, there are more elementary lifts, so-called theta lifts. Occasionally they coincide, but not always a trivial thing, because it's a theorem that a trace formal lift is the same as the theta lift, and sometimes they differ locally slightly. So there are subtle things going on. That's not the topic of this talk. The topic of this talk is I'm interested in L series. L series L pi of S with nice functional equations. Attached to these cuspidal automorphic forms. So it should be like Riemann zeta function. They should be a product of local L factors. So in the case of the Riemann zeta function, this is the Euler product of primes, and at the infinite place you have this well-known gamma factor, which is the L factor at the infinite place. So all together should make these functions behave nicely so that you have a functional equation. There's an easy factor, so-called epsilon factor, and then there should be a dual representation at the point 1 minus S, and dual here means in this case, it's very easy for a symplectic group. It just means the representation tensored with a one-dimensional character, which is the central character to the -1 composed with the similitude character, which is a character on the group. So this lambda G is a character which on the ideal value points goes to A star. And you can twist, and so it's if the central character is trivial, this is like Riemann zeta function. The dual thing is coinciding with the original guy pi. So I'm interested in L series with this property, usually a nice property one expects from these L factors. So in fact, there are 3 candidates. For this L. The first candidate goes by Nowotwowski. He uses that pi is generic. I didn't explain yet what generic means. The second construction uses good morning is the wrong time, I guess. The second uses this lift to GL4 plus G1. One perfectly knows what the canonical L function is for GL4, so we can lift there. And the third candidate is a little bit more complicated guy. This is Piatetski-Shapiro's L function, which is not an L function of pi itself, but an L function which can be only associated once you specify a certain additional datum. In fact, the same is true here. Being generic is also an additional datum of a so-called Whittaker functional, which you have. And not every representation has a Whittaker functional. If it has, then the representation is locally or globally generic, depending on whether this function is globally meaningful or not. But the same situation occurs here. But the difference is there is an abundance of such additional data here. These are so-called Bessel models for this pi. So in fact, there are even more candidates. There's the Langlands-Shahidi method gives another L factor, and so on and forth. But all these guys here tend to be the same, and it's in fact a theorem proven by Tato Bigas that these first 2 coincide. And in fact, the point is, therefore, because I'm interested in the principle of functoriality, concentrate on this function and the one on GL4. And I ask myself whether the principle of functoriality is true. The principle of functoriality is telling us, this is Langlands' philosophy, that you can push things once you have a morphism between dual groups. And the Langlands philosophy tells you how to describe this automorphic representation in terms of, well, finite dimensional representations of a so-called Langlands group, which is an unknown but conjectured version of the Galois group of Q. This is not known, but if this philosophy is true, you can push things, and the L factors, good and reasonable L factors, should be preserved. So,
candidates for what?
Say it again.
Candidates for what? You say there are three candidates for what?
For such L. You see, the L function itself is not uniquely determined by all these properties you propose. It's almost determined. If you have a functional equation, and it's in fact determined in all three cases, I wrote down unseen through, for almost all V, the unramified basis, these alpha functions are the same. But the L factors, the local factors, need not be the same at the bad primes at the places where ramification occurs. And therefore, you have three candidates, which might give different L factors. And the fact is, they give different L factors, and that's a surprise. And that's the purpose of this talk. Piadetti-Shapiro's L factors do not always coincide with those one would expect from the principle of functoriality. And that's surprising, and one should ask what happens, right? And that's the purpose of this talk. Okay, so the question is, do they coincide? I don't write the question. I gave the answer. Almost. But it seems not in all cases. So, and I try to explain what happens. So first of all, I want to give you an idea what these L functions are. I don't like to explain these constructions. I have not the time to do this. I believe that there is a nice theory of L functions, which is known by work of Harris, Taylor, and you have to be the canonical thing. There is nothing to discuss about this L function here. So, okay, so let me, how to define LPS, this Piaget-Shapiro L function. It has all the nice properties, functional equation, and so on. The first thing is, do Bessel models exist? So lambda always exists for global pi. Yeah, in our setting here. There's a very detailed analysis. I'll show you why they exist. And there's an exception, which is a metaplectic thing, which I'm not interested in, right? There's this model form of weight 1/2, which is singular. It doesn't have a Bessel model. And also the trivial representation doesn't have a Bessel model, a global one. So I'm looking at cusp forms, right? So, and not metaplectic. So in this setting, they exist. So, and I will show you how to construct them. So what is such a Bessel, or where is it coming from? The idea is very simple.
Yeah. What is lambda?
I give an example. Yeah, I'm just explaining what is going on. I think it's better than to give a theoretical thing. So this is a space of function, of L2 functions. I take a nice function in it, so-called automorphic function f of g. It's a function in this L2 space which sits in one of these summands. And of course, it's right invariant under g of q. And so you can consider matrices of this type. And you see this is an additive group here, multiplication. So in fact, you can, and this is here, X is a symmetric matrix, 2x2 matrix, A, B, B, C. This condition to be symplectic means that X is symmetric. And because this is ordinary Fourier analysis now, because it's invariant under the Q rational value points, and this is Q is co-compact in the ideals, you can expand with the Florrie expansion, and the Florrie expansion is the one which you very well know from theory of modular forms. It looks like this. You have the trace of T. T is this a 2x2 matrix, T1, T2, T2, T3, and well, so here's X. Have I forgotten something? No. What is psi? psi 0 is a character of A times Q, which is non-trivial character. Every choice is equally good. So you make this Fourier expansion, and this is the classical Fourier expansion people studied for a long time. Siegel studied this, the Siegel Fourier coefficient. There's a Siegel Fourier expansion. So these are coefficients now which depend, of course, function on G. And let's suppose all of these coefficients are 0, then the function f is 0. This is obvious because it's a Fourier expansion. But the point is there is a coefficient x such that determinant t is not 0. This is what I said. The form is not singular. It would have been a model form of weight 1/2. It couldn't be a model form of this group, but only of the metaplectic cover. So you find coefficients where they determine non-singular ones, where the determinant of t is non-zero. And once you have it, you see the stabilizer. So you have now, this is the nilpotent radical of the Siegel parabolic. The Siegel parabolic is the group of these block matrices in the group. And if you look here in the Levy group, call it M, say, the stabilizer of T, so conjugation by M operates here. And it operates on this character. And look at the stabilizer. The stabilizer of this character, psi trace Tx in M. This you can easily see is a torus, which is isomorphic, or which is the restrictions of scalar of K over Q of Gm, which means in down-to-earth terms, its points are just points in the multiplicative group of an algebra of degree 2 over K. So K is either a field extension given by adjoining the square root of the discriminant of T, or field extension, or K is Q plus Q. In which case you have a hyperbolic matrix T, say 0, 1, 1, 0. And then you can use a character of this. Choose a character chi of. Let's make it one. Okay. So this is an ideal class character of this quadratic extension field in such a way that, of course, if you now multiply by elements t twiggle from the left, you can arrange that you find it in such a way that at t twiggle g integral over rho t twiggle to the -1 t twiggle star is not 0. This is harmonic analysis again because well, one has to be really careful, but this is possible, right? It's obvious, particularly obvious in the case of field, because this is compact model center, but it's also true in the other case. If we find a character such that it's true, and in fact, what we have done is we have chosen a Whittaker model. This is a global model. We have thus chosen a global, not Whittaker, Bessel, sorry, excuse me, Bessel model. Lambda, which consists of this pair of the extension k of Q and such a character. With respect to the condition that this is not 0. And then if you have chosen these things, you can vary f. You see, now you let f vary, you fix this rho in the t and make always the same construction as I said, at this is also depending on f. You could write an f here because it's depending on f. And if you let vary f, you see this is a linear functional on pi, which is the sort for Bessel functional for this Bessel datum k, rho. Fine, so you see they exist, that's fine. And in fact, if you consider this, you see you can restrict this to the tensor product. You see it's inducing local Bessel functions. And the nice thing is, proven by, I think, Kwiatkowski, Shapiro, Nowodowski, and other people. I have forgotten. I'm sorry, I don't remember who proved it. These functions are unique up to a scalar once they exist. So for pi, locally, you can look at it locally now, because the global function is uniquely determined by its local restrictions, by patching it together in the tensor. For smooth, irreducible representation of G of the completion, a local Bessel function. Well, of course, this is always understood to be non-trivial. Is unique up to a constant for given lambda. Now you choose the corresponding local thing, the local algebra over QV and the restriction of the global character. It's unique for this given datum. Once it exists, it's unique up to a scalar. And so it's also true that for local representations you have a converse, but that's not important for this talk. Anyway, so you have this uniqueness, so you need not bother about the function itself, how it was defined. You just can fix your mind on the Bessel datum lambda, so this k in this row. Everything else is more or less determined once you have specified these things. Okay, so now I have defined what these lambdas are. And in fact, the L function produced by Peter Shapiro is constructed by a method which is originally due to Andrianov, and is using the ranking convolution trick. I just give the idea briefly, just to have a feeling that it's not complicated to write down the construction. It's more complicated to compute the local factors than writing down the global thing. On the other hand, it's a trick to make this work in higher dimensions. It's not so easy. So this is a rather peculiar trick so far. One can try to extend it, one can extend it even, but it's not so obvious. So we have fixed this Bessel atom for now, so I want to explain you how this L function now is defined. The method to construct is using Eisenstein series. To be honest, I don't know any method for constructing L functions without using Eisenstein series. This is not quite true. You might say that you can use Fourier transform, but I agree you can use both, but they're very closely linked to each other. So the Eisenstein series, I guess not everyone is acquainted with Eisenstein series, so I'll give you a very brief idea what an Eisenstein series is. I think modular picture, everybody knows this picture. This is the fundamental domain of SL2Z. And if you have a free wave coming in, which is invariant under just in this cylinder here, let's say it's not depending on x, so it's invariant, so it's just periodic, for instance, even it's constant, it's coming in here. But if this, you can think of it as a wave at a certain frequency. If this wouldn't have to respect this action of the SL2C, but only of the translation group, it would just remain this wave and travel through. But once it hits here, it's reflected and so on and so on. So this wave resonates in this cave. And what happens is some part of this wave, which is the standing wave, is added by reflections. And these reflections want to get out, but this cave is very long and small. So what it does, what you get by the reflection is something which is proportional to this guy. This is the only guy which has a chance to survive somehow, plus something which decays strongly. And why is this the case? Because this is a solution of the hyperbolic Laplacian operator, right? So the hyperbolic Laplacian operator is this guy. And the function doesn't depend on x. So it's obviously clear if you differentiate twice and multiply by y squared, you get a constant times the original function. But there's a second order differential operator, and it takes you a minute to see that there's a second solution, provided s is not 1/2. Then you have a log and something like this, right? So, well, this must be the second solution, which you see far outside, must be this guy up to a proportionality constant. The rest must be, well, that's a physical principle, it must be exponentially decaying. And in fact, it's true if you compute this carefully. And then you see it's something very simple in this case, or in the simplest case. Something, I've forgotten, maybe I'm mistaken now. I should have looked it up. As far as I remember, something like that. It's some Whittaker function, which can be some canonical Bessel function, something like that. I wouldn't take this for granted. Maybe there's a constant, something like that. It depends on some normalization. But you see, it's very nice. It's like a usual Eisenstein series should behave. Some coefficients people who study modular forms are familiar with. But the essential information is of this computation. And I think that's important. Is if you really compute this, you get a factor of this type, some epsilon factor, similar like for functional equation, something of that type. And that's important. That's missing some guy, some overall proportionality factor, which is more or less the same thing. Then the funny thing is now, because this function it's orthogonal, well, it takes a minute to understand it. It's orthogonal to our cusp spectrum here. This is a two-lines argument. So because it's orthogonal to everything, by dimension arguments, you see that if you switch s from 1 plus s to minus s, so you see that this ms, it's not hard to see, that this is the same as this. By spectral theory argument, orthogonality to, it's not that easy, but it's not hard to see. And this implies the functional equation, so we can extract now this factor by multiplying this, you can extract this, and this gives LS plus functional equation. This was used by Langlands, this Eisenstein argument, and Shahidi. And this is a powerful argument to produce L series, but also produces, if you plug it in, a functional equation of the Eisenstein series. The Eisenstein series I explained here. This is the Eisenstein series. Has a functional equation. This is this thing. It's a function on the above space. And it has a functional equation. I normalized it in a stupid way. You see, I put in the 1/2. If you normalize it a different way, it gets the usual form, s goes to 1 minus s. The spectral theoretic correct normalization is this, because in this normalization, the operator becomes unitary up to a normalizing factor, which is written here, once s is on the pure imaginary axis. Anyway, so this function has a functional equation, and it's a function of g. And the Rankine trick is a trick where you take an Eisenstein series and integrate it against something which is interesting, a cusp form. Usually it doesn't work to integrate against the cusp form because it's orthogonal to cusp form, but you throw in an additional factor in a clever way or restrict to a subgroup and so on and forth. You get something, if you are very, very lucky and ingenious, which works. And this is sometimes the case, and these are the rare cases where you can produce L series by Eisenstein series and Rankine convolution. And that's one occasion, this Andreamer construction. So I have now everything together to explain how the L factor is defined. And once I define it, I can discuss some of its properties. So I think it's important to see how it's defined. Otherwise, one doesn't get a feeling for what it thinks. So I need some notation, perhaps. Okay, no, I skipped the notation. The point is this. In this group G is B4, we found this group, the stabilizer of T. I write it in a stupid way. We call, in the Levy group, I try to find the stabilizer. This makes up a group, so this is determined by this and so on. This gives a certain group, and I take here the orthogonal complement. Well, there's a certain subgroup which I call T twiggle times R twiggle. I'm sorry for the notation. This is just because I'm too lazy to write down this all the time. And in fact, R twiggle plus the kernel of the trace T map is the space of all 2x2 matrices which are possible here. So this is a subgroup in here. And I introduce two other candidates, which is the matrices of this type. They are not in this group, which I call T. Lambda in our ground field. I think that's clear what is understood. And this complement here, I call S. And I have S, and in fact, TS normalizes the easy computation, normalizes this group TR. And TR is exactly the group we used in the definition of Bessel models. You know, I have made an integration over this integration and the picking of the Fourier coefficients involved these two groups. So essentially, these groups are involved. These were not involved, but in fact, this normalizes this group. And this is important. And the idea now is to find a group H in the symplectic group, and this group H is, well, its F-valued points are the isomorphic to the G in GL2. K is this imaginary, this quadratic algebra of order of dimension 2 over Q, with the property that the determinant of G is in Q star. This, in fact, is a subgroup, and in fact, this group which defined the Bessel model is the Borel subgroup. Of this group H. So the idea now is the following. The L function is defined by consider. So we are at the end of the story. One considers the following construction, which is we send F, and this is a function from pi. I simplify the picture a little bit. I integrate over the ideals of H, this group, divided by HQ, and the center of the big group G. Our automorphic function, we restrict from G, where the cusp from here, restricted to the subgroup. Integrate against an Eisenstein series, which is defined on GL2. This is almost GL2 in the way I explained before. I did it in the case of a Q, but we have to do it over an extension field. Of course, I'm cheating a little bit for the sake of this talk. The situation is slightly more complicated than in this picture above. I sent the most easy free wave into it, but in general you can send an ideal class character from above. And also you have many Eisenstein series, not just one. Let's pretend this problem is not there, and let's focus on F. But in fact, there's a lot of degrees of freedom here. This is fixed, but here there are many Eisenstein series. But these functions altogether, as a function of S, have a meromorphic continuation. So for each F and also for all these additional degrees of freedom. And then the point is, at some points of S, they are only meromorphic, but not holomorphic, have poles. And the global L function is defined as the most economic L factor, whatever this is, which is a regularization which makes this non-zero and holomorphic. I think that's enough for getting an idea what this L factor is. It's defined by regularizing this guy, which has a nice functional equation, but is only meromorphic. And so you can somehow work this out. This is an exercise once you have the idea. Okay, so now I've defined these functions. They have all the good properties one expects. Functional equation, decay in vertical strips, and so on and forth. Epsilon factors, they factorize locally, epsilon factors factorize locally, and so on. So the question is, does it coincide with these representation if pi is generic? The answer is no. It's no. The answer is no. But it's almost correct. And I explain what is going on. That's quite interesting, but it's not a real failure. Because, in a sense, the picture is this. If you have a generic representation and fix the k on half of the Bessel atom and just try to vary rho, then you find infinitely many possibilities for rho. And as a matter of fact, there are most finitely many bad rhos where the L factor by Shapiro differs from those from the upper group. So for generic representations where these are defined, the point is there are some singular cases where it differs. You can calculate them. We calculated them in a recent paper. But you find out, you can understand the structure, why they fail and how they fail. I will tell you something according to this later. So, but what happens if you have a representation which is not generic? Then you don't have any of these guys. You only have this guy. I know of no other, to the best of my knowledge, of no other possibility to make up a global L function which for non-tempered representations, non-generic and even non-tempered representations, give anything except this one in this case. So it's a good testing example. And you see this interesting group of representations which has nice geometric importance here. It's related to the Picard group of the Shimura variety and so on and so forth. And these representations are non-generic, non-tempered. So these are not obscure objects. They are very natural there, and from the point of algebraic geometry, they are important. Same here. They're also important for geometry. They describe the intermediate Jacobian in the middle cohomology. And these guys here, they are mainly generic, but there could be some harmless problem, which is not so serious. But the problem number two is for non-generic representations, and that's something I don't really understand. For some non-tempered representation, the factors, also this is a local question. There's a unique Bessel model, or two Bessel models, locally. There's a unique K and two rows. And for both, the local L factor is something that is different from that what you obtain here when you apply the principle of functoriality. That's very strange and confusing. So the first reaction is either there's a mistake in the calculation. I don't believe it, so it's a fresh paper, but I think we did this carefully because that is consequence. I think that's not the point. The point is something different. What turns out to be the case, so I checked there are 4 cases where this happens. I checked in 3 cases that something interesting happens. The cases where this fails, one can show that there is no automorphic Caspel representation, which locally has this. The easiest case if this representation has no unitary candidate, then it has died because we have an L2 space. But there are cases which are unitary, and there's no a priori reason why they shouldn't occur, but they cannot occur because one can show this. So what I think might be the correct answer, it could be that sometimes there's a failure, but it cannot be globally realized. But I have no idea whether this is the correct answer, but it's a very interesting question which shows up here. And in the last minutes, I will just give you a picture of what I explained now in a rough way, in a little bit more detailed way. I'll just give you the cases of possibility with a little more detail and try to explain what happens. So in order to do this, let me just give some rough indication on the structure of this Piatitsky function.
Degree 16 L function?
Pardon?
What is the degree of
Degree 4. This is a Spino L function.
for F, and then there is degree 4 corresponding to, it's it's some kind of Rankine product. This L function which intervenes in this calculation should be some Rankine product of f and the Einstein series.
Yeah.
And therefore it should have maybe larger degree than.
No, it says it's the degree 4 L function. This is the standard L function. This is the Spino L function. Degree 4.
Degree 4. And standard will be degree 5 with trivial effect.
It's the standard L function of the JSP4. It has degree 4 and it coincides with the GL4 L function at almost all places.
Rho doesn't play a role.
Pardon?
The representation rho of
the row. It was a statement of Novodosky that the L function of him does not depend on. Is equal to this one independently of rho. This is also not true. So it's almost independent, but they are finitely. Yes. It's almost. I explain it in a minute. The cases where there are differences, I will explain. So there's the following rough structure. This is Piateschi-Shapiro. This L function is composed globally and locally of two parts, a regular part and an exceptional part. This part is harder to compute psychologically, not in fact, it's not so difficult to compute it, I think, finally. But the conjecture, he conjectured, PS conjectured, and this conjecture we have proven that this factor occurs, well, it occurs even only if it occurs locally, right? The product of these local factors. It occurs locally, and this is the form of the conjecture of PS. It's always understood that it means a non-trivial. I don't write, of course. This period function is again a homomorphism on this representation space, which is H QV invariant. And H is this almost GL2 up to this determining condition, functional to C. So this is a subgroup. Recall, I just erased it, unfortunately. This was a subgroup which is a subgroup of GL2 over this extension algebra K. And it's a subgroup in here, so we can restrict this representation. It's better to write it like restricted to H of QB. So this is an equivariant thing with respect to some character of H. I write it rho. It could be an arbitrary character, but in fact it turns out when it exists, it's essentially the rho of a Bessel model, so I use the same notation. And in fact, if it exists, we can show it's essentially unique. Even the rho is essentially, it's unique for a fixed rho up to constant, but also the rho is unique up to possibly CM multiplication. So if there's a CM representation, you can twist and it's the same. You can twist the character, but it's the only modification allowed. So these functions are unique if they exist, but this exceptional factor sees whether such a period exists. And this period, in fact, if you think of it, it's something like really integration periods if you do it in geometries. Cyclic integrals come from this. If you integrate over a Picard surface, then you get, in practice, these functionals. And so this is true. One can even say more.
Any set of primes, or it can happen at all primes?
If you have a Saito Koraka, well, if it happens at all primes, yeah. You have a global functional, yes.
Generically, it's a
Yeah. So if you have, in a local situation, I just write down for which local representation this is. You can see the characterization is exactly it's related to Saito Kurokawa locally, right? But I've just forgotten what it. Wait a minute, I have. Yeah, that was the criterion. So the proposition is this: the H period functional. For some Bessel model, right? If and only if. So what was it? Yeah. It's either a local Saito Kurokawa lift or a local Sutri lift. So this is exactly this corner here. It appears globally. And if you have a global representation sitting in here, recall these are non-tempered, non-generic representations here in this families. So you can sort of locally characterize them very nicely by these period functions. And in fact, globally, they do not satisfy the Ramanujan conjecture. So these terms have additional poles. And in fact, with the residue as the poles define global functions of that type. Okay, but you can completely locally, it's not clear whether ever local representation can be embedded. Of course, if it's Caspel, you can, but it's not always possible to embed a local representation into the global one, unless it's Caspel or say almost Caspel in some sense. But there's a purely local criterion to determine this this behavior of the exceptional pole, which controls these periods. So the regular things, I have no time at all to go into any computation ideas. I just state in my final conclusion. Sorry. Here's it. I just give you a rough outline what happens. So you can divide all the local representations in 26 families. So you have 12 generic ones. One is the family of all cuspidal representation. From one certain point of view, the most interesting, but in this case it's behaving like. And 5 good cases, whatever this means, where there's no difference in L factors and so on. And there are 2 plus 1 fully induced cases. I have no time to say what this means, just to give an idea. For Saito Kurokawa companions, I have to explain what this is. And I write down, this is a classification which is due to Tadic and Celia, just to make it specific. It's these guys. And there's also some twist, which is isomorphic to this. This is a CM representation with a quadratic character. It's important to write this like in this form because to explain what is really happening, this picture here is useful. There are 14 non-generic families. There are 2 cuspidal families, they are not generic. There are these 2 cuspidal, which together with 5 others give Saito Kurokawa representation, local ones. And these 2 cuspidals, they are in brackets, plus 2 others give local Sutri. These are the local analogs of this piece here. Then there's the 2, 5, 7, 9. Then there's one family is the one-dimensional representations, which are not interesting. Then there are two families of type 9b and 4b, and there are two families called 3b and 4c. And the problems, or the interesting thing where L factors appear not to be match compatible with lifting, they are these two. And all Bessel models here, there are only finitely many. So if the representation is not generic, it's only finitely many Bessel models for a given k. And it's rather rigid. Sometimes it's only a unique k which does the job. In this case here, in the 3b case, there's a unique k and I think 2 characters, rho and its Galois conjugate, which does the job. So on this side, there are no problems at all, except this family, certain rho, give Bessel models where functoriality doesn't work. However, this is not a problem because you have for fixed k, and these problems only occur on this side if this algebra is split, which means k is f plus f. So which means the Fourier coefficient we picked was a hyperbolic matrix, a hyperbolic plane, and then the orthogonal group is non-compact modulated center. And there are all the problems by split case, and there are infinitely many split Bessel models, but only finitely many. In fact, a unique one makes problems. Certain rho make problems. But however, in this case, we can show that these Bessel models never can occur globally, so they are globally irrelevant. They never occur as Fourier coefficients of a modular form in the cuspidal spectrum. So it's interesting to see that the failure of this lifting shows that certain forms cannot appear. And here it's certain Bessel models cannot appear. So in fact, we can show that these, this, and this cannot appear by such principles of L functoriality. They don't appear in the spectrum, but if you forget Langlands functoriality globally, just look locally, you are startled because something is going on that I don't understand. It's the only way to define local L factors from the automorphic side, because you are in the non-generic side of the picture, and all the other recipes don't work, and somehow there seems to be something interesting. But however, all these cases so far, we can show they can never occur as a local constituent in a global cuspidal form. And the same holds here as a variant of the picture. If there are problems here in this family. There's a second family with problems. The companions of Saito Kurokawa. And I will just show you a last picture at the Archimedean place, what this means. So these are also cases where a global cuspidal form, this is a corollary, a global cuspidal form can never have, belonging to these companions at some place, can never have a split Bessel model at that place for the trivial character rho. This is a certain property of Fourier coefficients of modular form, which is a consequence of this, which is for me surprising, but I think this is the answer to this riddle. And the only form I didn't check so far, I think I can show that it doesn't exist, but one has to distinguish between global Whittaker model and so a form which is locally generic at all places need not be globally generic. So the notion of a function that is globally means you can realize it really as a function in the Fourier expansion, which is globally non-trivial, and same with Bessel model. So you have to be very careful about a Bessel model is a global Bessel model, or it's just a Bessel model which locally considered, each local factor is a Bessel model which exists for a local representation. And there is no, yeah, yes. The local Bessel models behave not nice, but for the cases where they don't behave nice on the generic side, there is no global Bessel model realizing this. But on the non-generic side, you have a problem. So the same principle show you that there cannot be an automorphic form which has this local constituent P nu, because otherwise, because there's a unique local Bessel model, if it would exist globally, the same principle gives a contradiction showing that this pi global can never realize this guy, or this guy, or this guy. Perhaps also not this is the last exception. As I said, I'm checking this. Is not. I wouldn't like to write it down because I'm not 100% sure this is correct. So it's a bit tricky. So this case is a bit tricky. So one has to be careful, and I won't say something which I would regret. So, but that is what I expect at least. Yeah, that's the thing. But if you look at the local principal functorial, you have a problem in a certain way. Otherwise, if you find another, let's say you are lucky and find another L series 4, which gives a local and global construction with functional equation, you can show that it must coincide with Piaget-Shapiro's on the non-tempered guy here. This you can show from our computations. So you see, a little bit of trouble remains, for me at least. The principle of functoriality is subtle in some sense, if these corrections are really solid, and I believe strongly in solidity. So I wanted to say something at the end, but maybe I'm out of time. I'm sorry for that, so I stop my lecture here.